start from, yeah, let's say start from this unit step functions. Okay, so basically what this Heaviside function or unit step function is, we are having these two conditions. Okay, so we have some interval, that is when we look at the function, it will be 0, and we might. And the other part is equal to 1. So, for example, if we have our function 2t minus 3, if you write down in a Heaviside, for example, 2t minus 3 and a Heaviside, t minus 1, which means that at this t equal 1, from 0 to 1, it will be 0, and from 1 to infinity, it would go to this line equation as the function itself. Right? So that's the beginning. And then we could tweak this formulation to more complex, and we could write down these two functions g and h, which we have now. We could write this f in terms of g minus g of this Heaviside, and plus h and Heaviside. Okay. And for example, this part here, 0, g, 0, and right here, and then becoming like this. And then this is an example. We have this graph, this curve. Okay. So we could write down the functions as 2 minus 3 Heaviside t minus 2, and plus Heaviside t minus 3. You could see from the interval here. Okay. See from this interval. Yeah, while waiting, the window suddenly update by itself. Okay. And then we could solve this. Okay. Take Laplace, and Laplace of the Heaviside, you can directly write down the e with power of these 2 coming from this 2 here. Okay. So negative 2s over s. Okay. I think I have written somewhere. Oh, here. Okay. So this is the key points. Key points for Heaviside. You can write Heaviside as this, which particularly from here, and then you can go make some rearrangement, and then yeah, for most of the part, if you can take Laplace, then you can take the inverse Laplace. Okay, so you can take Laplace inverse of this, and it's actually, we could think from here, we take Laplace and we get this. Okay, and then we take the inverse of this and we get this. Okay, so why we need to take the inverse? Because at the end, okay, at the end of the day, we want to make the function back to the original variable. Okay, so every time we take Laplace in differential equations, we usually start from t, we transform into s, solve algebraically. We can solve in terms of algebra, and then after we get we call the capital YS, and then transform back using the inverse of Laplace, and then we got the t. Then this is the solution of the differential equation. Okay? So if you compare with the method that we did in the first order differential equation, the higher order differential equation, using Laplace seems more simplified. Okay? For some cases, it's more efficient, more effective, and you get easily the process. You could process them, process all of them easily. Okay. Yeah, this is examples. I think also in the video. Okay, let me check. Okay, it's just restarted. Okay, and then what else do we have here? Yeah, another alternative theorem. Okay, sometimes if we take this part here, maybe it's too complex or too complicated. So we could rewrite and write in terms of, well, to differentiate, we call this G now, and then have sine t minus a. And then we could have this, and this becomes Laplace G of t plus a. Okay. For example, we could take this and this happy side, take Laplace, take Laplace, also take Laplace here, Laplace there, for each happy side. Okay. Yeah, I think you could check in your notes for the happy side. Yeah, you could do this two ways. Okay. First, the first one is the first method as in the previous one. The second one, you're going to change this into the this form. You can change to this form, which is, I think, more simplified, and I think to process out all of those is not too complex. You could just take, so whenever you have t squared, t minus 2, rearrangement of this becomes t plus, actually you could see from this t, it has a square, so we are going to substitute this and make it out into this t plus 2 as we have in the alternative theorem. Okay? And then we solve this one by one, take Laplace, and eventually we'll get the same result as the previous method. The previous method sometimes too complex, too long to write. Okay. Okay, perhaps we need some exercise, but I think I will prepare. Yeah, supposedly last Tuesday I wrote out the exercise, but I haven't had any time. So maybe within this weekend I will provide some exercise. Perhaps it's maybe homework, so you can work that out. So the homework is about Laplace, inverse, Laplace of derivatives, translations. Okay, those three. Okay. Let me start for today's class by taking all this. Okay. So yeah, we end up until here. I'm actually not really finishing out this part, but I do believe I've solved all the key points, so you just compute the rest. Okay. Okay, what I want to share today is the we call this section is about additional operational property. Okay, so first we are going to take you to, we call the derivatives of transform. So imagine that we have the fs, right? So imagine that this fs is our Laplace, okay, Laplace. But what we are going to do is we are going to take derivative of this f. Okay, so we take derivative, so we write TDS like that. Okay, which means we are going to take the derivatives of the Laplace. Let me write Laplace in terms of the definition. So integral from 0 to infinity. Right? And then we can try to force out this DDS inside the integrations and making this DDS as a partial. So write down here. Let me write with the Leibniz notations. Okay. So by taking this partial, we are going to take the derivative of this s here. Okay. So take that derivative. We will have negative e with power of negative st. Okay, so this will be negative okay, and actually what we have here is, what is this actually? If you remember. This is the translations, right? Oh, should be right with this t, because t is, in our case here, is not going to be derived. Okay. Okay, now we have this TFT. Okay. In the original Laplace, this is supposed to be just f of t, right? So this means what's happened here is, actually this is negative of Laplace of TFT. So if we take a Laplace TFT, this is going to be negative TDS Laplace f of t. Okay, maybe to make sure that we confirm this, I forgot to write here that this capital F is Laplace of this f of t. Okay, so we take from the result here and take the derivative, and we simply get this result. So whenever we take this Laplace of TFT, then it could be this DDS, Laplace f of t. Okay? And then what's happened if we have Laplace of t squared f of t? Okay, so if this is t squared, we could think that this t squared is t by t, right? T multiplied t, right? Which means that we could think the first t as the DDS. So this is DDS TFT, and this t will be DDS. So this will be the second derivative. Okay, it will be second derivative. Or not the second derivative, it's squared. Okay, sorry, squared, not second derivative. So this will be negative DDS Laplace TFT. Okay, and then you could take this negative DDS Laplace. Oh, it is the derivative. Okay. f of t. And this will be d Okay, so we could write the formulations for some n, so t with power of n. Okay, so if capital F is Laplace that and n start from 1, 2, 3, etc. Then Laplace of t power n f of t is -1 with power of n. This is because of negative, so negative, negative, positive. So negative, positive, negative, positive, right? And then d with power of n So we can have repeated derivatives. I think to give you more clear and maybe safest way, perhaps we could just take one by one first. So take derivative, then take derivative again. Maybe that would be safer. Okay, just a example. Or maybe let me make the box first. So you could, if you take the f, maybe using the e, you remember the e. We could have translations. But we can also take with this theorem, so you could have more options. And my suggestions, if you want to make to write down as a notes, you could prepare another notes for all the summarize for all the structures. So you could have. So if you have Laplace something, you could think not only one way, but maybe multiple ways. Okay, let me show you. So first, if we take the Laplace of t sine, let's say k as a constant k, we could start with the taking f of t sine kt. Okay. Then as a Laplace, we could take the capital F as, for sine is k, right? And then s squared plus k squared. Okay. And since the n is 1, okay, t, just t, not having any power. So we could write down the Laplace t sine kt. This will be negative dds of Laplace sine kt, which means we are going to derive the this k over s squared plus k squared. Okay, we are going to take the quotient rule. So take the s squared plus k squared squared. And then 0. This is supposed to be minus, but because we are multiplying with minus, we are having the plus. So plus 2s and k, or 2ks, right? So we are having 2ks over this s squared plus k squared squared. This is Laplace of t sine kt. Okay, so you could imagine if we take maybe t squared or t cubed, then we are going to derive again, okay, and again and again. So we are going to derive this, and then we get more, and then derive again and again. Okay, and then what if the let's say t with power of n, and then we have e with power of at. Okay. So if we take Laplace of this structure forms, we could have at least two methods to evaluate. The first one is the translations, the shifted method, and the other one is we derive. Okay, let me show you. Let's say we are going to take Laplace of t e with power of 3t. Remember, whenever we multiply with e with power of something t, we are going to have a shifted, okay, or translations. Okay, so this is actually Laplace of t, and then we shift it from s to s minus 3 according to this a here. So this will be, this is 2, then s minus 2, this is 4, s minus 4, and so on. So Laplace of t is 1 over s squared. Okay, so 1 over s squared, and then we shift it s becoming s minus 3. Then we can substitute. Okay, we can just substitute. So this will be equal 1 over s minus 3 and then squared. Okay. Now, because we now have the derivatives, the new method, then we could take that as well, and we could compare the result. So we could take this negative d ds, okay, and then Laplace of e with power of 3t. Laplace of e power of 3t is just 1 over s minus 3, right? So this is negative d ds of 1 over s minus 3. 1 over s minus 3 we derive becoming negative 1 over s squared, right? Having s squared, s minus 3 squared, right? So this will be 1 over s minus 3 and s squared, the same results. Okay, so you could choose which Laplace you are going to take on. So Laplace is very flexible. Laplace is very flexible. There are several ways, several interpretations, and all interpretations, as long as they are consistent, and you can prove that okay, this is just the same thing, and you can choose which method you are going to take. For example, this one here, we could think that if we multiply t with something with e, this e will be shifted this Laplace t, right? And we can also interpret this as, okay, we have t with power of 1 and then some function here, which means that this function, the Laplace of this function, we are going to take derivative of with respect to s, as we discussed at the beginning, right? But then, okay, the same result. Okay, so you can choose methods. Okay. This is derivative transform. A derivative transform. We call the derivative transform. There are another transformations, one more in these sections, which we call the transform of integrals. Okay, to begin with this transform of integrals, we are going to start with the new terms we call the convolution. Okay, so if functions f and g, they are piecewise continuous, on interval, the positive interval, then convolution of f and g, denoted by, we write the convolution as f. Convolution is like a asterisk like that. Okay, that is defined by integration from 0 to t f of some other variable, we call the dummy variable, but because I put t, or we already have t in our normal equations, we're going to write another variable. This will be the variable of tau, okay. G t minus tau, d tau. So the convolution f and g is a function of t. Okay. Remember that the form is actually similar to what in the fundamental theorem of calculus, right? If we see that this is actually, it can be any variable, but this to differentiate with t we have here, then we need to take this into different variables. Usually in the calculus, when we learn the fundamental theorem of calculus, we have t here and x here, right? But now we have t because usually we are taking t in our method, f of t, right? So we need to have another variable here. So we take the tau. Usually the convolution also can be written as a generalized product of f and g. Okay. This is convolution. Okay, let's start to take the how we use these convolutions. Okay, we haven't yet started the Laplace. This is just convolution first. Later we will have the Laplace itself. So if we take e to the t and convolute it with sine t, then this will be equal to 0 to t. This is e with power of tau sine t minus tau. Okay. So we're going to take integration by parts, right? Integration by parts. Sine is becoming negative cosine, but negative, so it's cosine. So this will be maybe one more. This will be cosine integrate becomes sine, but negative sine. So this will be, is this too much? Yeah, I think okay. Okay. This will be 2 this is e to the t, this is 0, oh, wait, wrong. Supposed to be t is 0, so e to the t minus 0, 1 cos t, right? Okay, and then plus 0 minus sine t, right? Yeah, I think this is correct. So this part is half of this, all of this. Okay. So we get that this will be equal to half okay, this is just to familiarize with the convolutions. Okay. Now if you take Laplace of that function, then we are going to take Laplace of half e to the t minus cos t minus sin t. Or we are going to take one by one. So half Laplace e to the t, and then minus 1/2 Laplace of cosine t minus Laplace of sine t. And then we can take this half 1 over s minus 1 and minus half s squared plus 1 minus half 1 s squared plus 1. And we can simply take all this s minus 1 and s squared plus 1. So this is half s squared plus 1 cancel this part, cancel, plus half s, this is cancel. So half plus half is 1, so this will be 1 over. Okay. Okay, another important in the convolutions, so property, is that if we have okay, let's say we have this, okay, we could write and take the other way around and switch the inside of the functions, and this is still correct. Okay? So we could write down the f convoluted with g is equal with g convoluted with f. Okay? So they are commutative. Okay. So the Laplace, we are going to end Laplace until we reach the Dirac delta functions, and then that will be the all the topics on Laplace. Okay, I will end this today class with the theorem, but I will explain the theorem on next week. Okay, we call the convolutions theorem. So this is if f and g are piecewise continuous on the positive values and of exponential order, okay, then Laplace of the f convoluted with g is equal to Laplace of f of t and then Laplace of g of t equal to capital F and capital G of S. So this will be the theorem. I will explain this theorem next Tuesday. So the convolutions, when we take the Laplace, we could think that convolution is to take the Laplace of h and we multiply. Okay? So we are taking the product of the convolution. When we take Laplace, we are just multiplying the result of all the h Laplace of the function. And then sometimes, when we have this definition of the convolutions, we could transform, like for example, if you are known to have the functions, then you could reverse and make up the convolution and then take Laplace. Yeah, it's a new term, but I hope you can get used to this convolution. Yeah, it's interesting, right? It's like the math. It's like a multiplication, but